Hey all, Shemai Paub. This is Idna, and today I'm going to walk you through a HackTheBox Sherlock called Cafe Poisoning. It's a medium difficulty Sherlock from Surex58. I've probably butchered your name, I'm really sorry. But it takes us through an investigation that starts with a coffee shop style machine in the middle attack, and then goes on to include some nice Windows forensics and malware analysis. Let's get cracking. Okay, so here we are on the HTTP Labs platform. I'm going to go to Sherlocks, and I'm going to start a search for Cafe Poisoning, and we can find that here. So we can read through our scenario. While grabbing coffee at a cafe, I connected to a public Wi-Fi and started a Windows update. The process never completed, it just kept running. As a digital forensics expert, can you help investigate? Now, I'm pretty sure that we can. The first thing we need to do is download our artifacts to investigate. I'm going to copy those into my clipboard and move them over here into my Windows machine. So I'm using Windows for this. Later on, we're going to be using a lot of the Eric Zimmerman suite of tools, which are much more easy to run on Windows rather than trying to adapt them to run on Linux. It's just easier to do this on Windows sometimes. So just waiting for that to download, and we can open up our folder. Now I'm going to extract these using 7-zip, and the password, you can get the password by clicking that there. However, the password for Sherlock is always HackTheBox. Okay, we can look in that. We've got an artifacts folder, we've got a packet capture, and we've got another archive folder here. So let's extract that again. And inside here, we have got what looks like a CAPE Windows artifact collection. So a bunch of useful artifacts from a Windows device, which is the device we're going to be investigating. Our first question is, the attacker performed a host discovery scan to identify devices on the network. Provide the start time of this activity in UTC. Now, we're going to look at our packet capture for this. A way that devices find out where other devices are on the same network as them, or rather who the other devices are, is through a protocol called Address Resolution Protocol. So that's known as ARP. So I'm going to put this filter in here and start to explain some of that. So on a layer 2 network, so that is like a local network. We're not talking about internet here, we're talking about devices on the same network as each other. They need to know about their neighbors. They might need to send traffic to their neighbors, need to know where they are, what is their address. And they use ARP for that. So here we can see 192.168.1.15 asking who has 192.168.1.90. So they know they need to send some traffic to 1.90, but they don't know who has that. Now the who here is the MAC address related to the network card that is on the device. So they know they need to send that. The other device needs to tell them, I'm over here. And that's what ARP is doing. With ARP, you can do what's known as an ARP scan to discover devices on the same network, or more information about those devices on the same network. So you can see that happening here. This 192.168.1.11 is sending out a lot of ARP requests for devices, or for IP addresses in the same subnet as itself. It wants to know who has this address, who has this address, who has this address. This is not normal behavior. You wouldn't typically see so many ARP requests coming from the same device in such a short time period. So these are all happening within the same second. So this is almost definitely an ARP scan. So that is what's happening here. If we go back to our question, the attacker performed a host discovery scan to identify devices on the network, provide the start time. So that we can see this is the scan here. We want to know when it started. Our attacker device, or the device doing the scan, is this 192.168.1.11. You can see that because it's the one making these repeat requests. We can add to our filter by, in the packet details here, expand address resolution protocol, find the sender IP address, right click, apply as filter, select it, and that will just show us all of the ARP requests coming from 192.168.1.11. So that gives us an idea of when this started and everything that went on after it. So you can see it's all these requests coming from it. That's it, to try and discover everything on that network. We need to know when this happened. The time here is, by default, Wireshark uses seconds since the first capture, since the first packet in this capture. So this is 800 seconds since this packet capture started. We don't want that format. We want the format in UTC, and specifically this time format here, which is year, month, day, hours, minutes, seconds. We can tell Wireshark to display in that format or very near that format, like this, view time display format, and then UTC date and time of day. So here we can see that has now changed that, and we can see that all of this started at the 10th of March 2025, 7 minutes past 9 in the evening and 5 seconds. We can extract that information a bit more easily by dropping down the frame. Yeah, we can just type this in manually if we wanted to, but I'm a little bit lazy. So I find this, I right click and I choose copy value. And then in the answer here, I can paste that in. Now we don't need all of these details. We only needed everything up to the second. So after that dot is all milliseconds and time zone information. So we can get rid of that. And the other change to the format is, instead of a T, HackTheBox expects the format with a space in there. And that should be our first answer. That tells us when the ARP scan started. Question number 2. The attacker launched an ARP poisoning attack. Provide the start time in UTC. Now, an ARP poisoning attack is when these devices on the same network are talking to each other, and we can see here that 192.168.1.11 asks who it is on this IP address, 1.106. It's dependent on the right device telling it, I am over here. So if you imagine, if someone could intercept that, someone could get in the middle of that. So if you imagine 3 people in a room, I want to speak to John, but Fred is also in the room, and I don't know which is which, and I say to you, which one of you is John? Fred answers first and says, I'm John. I'm going to tell John what it is that I want to know. That is the nature of an ARP poisoning attack. The attacker basically responds to an ARP request before the legitimate host does, and the sender then assumes that that is correct, and they will send the traffic that was intended for the legitimate host to the attacker first. An attacker device will often pass that information back on to the intended host so that they can be a bit more stealthy, and they can sit in the middle of a conversation and they can find out what's going on in between these two devices. That's effectively an ARP poisoning attack. We want to look for that in here. We will keep scrolling through. We'll still keep ARP. Oh, actually, I need to go back to my original filter. I don't just want to see the ARP requests from the attacker. I want to go back to all of the ARP traffic. So let's knock that back a little bit. So we can still, this is the ARP scan. So this is everything coming from 192.168.1.11. As it's still doing its discovery scan. And as we get a little further down, we will start to see some additional things. So here we can see some ARP responses, ARP replies. And we should see that in here somewhere. Maybe we don't. But so this is the replies. So we can see here 192.168.1.43 is at this address. So that is an ARP reply. What we can see if we look a little closely at the detail here, so we know 192.168.1.11 is the attacker in this situation. I'm just going to close that, and we can see the MAC address of that is this 0800279B 8B BD. Now if we look closely here, this is that MAC address there is the same. Go back to that. So this is actually our attacker responding to say, I am at 1.43. They'll say, I am at 1.90. I'm at 1.43, I'm at 1.90. So the attacker is sending these replies, hoping to get in there before the legitimate device. So down here, we can see, if I just scroll a little bit further down, there's also another reply from this device saying that they are at 1.43, but our attacker got in there first. So they have intercepted that, and they are now the machine in the middle of that conversation. So that is the ARP poisoning attack. The question is asking us when that started. And this is the first packet here where that seems to be happening. And that is the timestamp we're after this. So again, I will expand this. Right click, copy value, and make the same change here. So remove everything after seconds. And we've got our second answer. So we can see here, roughly 30 seconds after the discovery scan, the attacker then did their ARP poisoning attack. What MAC address did the attacker use during the ARP poisoning attack? Now, we just saw that. That's this address here. So that's quite a nice simple one. We can just quickly grab that from here. So a little bit easier to get it from the layer 2, I think. Copy value. You don't have to do it that way. You can type it in manually. You can copy it from any number of these other places, as long as it's the same value. So now we know the MAC address associated with the attack. What is the gateway IP address of the network? Now, this is a little bit of a tricky one, I think. We can see, where is it? I think it might be right at the beginning of this. Actually, sorry, a little bit further on. There's some traffic in here that is kind of indicative of it being a gateway. So, right, here we go. So these ARP announcements. So there's a couple of announcements here that help us to identify what the gateway is. If you imagine you are the default gateway on a network, you actually need to know who is on that network. You need to be the one that is up to date, because it is your responsibility to make sure everyone is getting the information they need. You're receiving traffic from outside of that network, let's say from the internet or other segments of the network, that is intended for devices on your network. You need to know where they all are. So you are going to be on the ball for this. What you're seeing here, this ARP announcement, 1.43 has just joined the network, and they're sending out a gratuitous ARP, it's known as a gratuitous ARP, and saying, hi, I'm over here, I've just joined. Immediately, the gateway is saying, okay, who are you? You can see another one here, gratuitous ARP, 1.11 has just joined the network, straight after 1.90 is saying, okay, who are you? So it's not 100% accurate, but I think those two things happening in a row there gives me a good indication that 1.90 is actually the gateway of this network. We can confirm that by entering in as our answer, and then we will find out. And it is. But yeah, so those parts of that packet capture point me towards that. Like I said, it's not an exact science there, but on a network that we're seeing here, it's quite a small network, that would tell that to me there. Which spoofed domain was accessed by the compromised user? Right, so we're jumping on a bit now really in our story. We know that the attacker has done a discovery scan. They've found some devices. They've stuck themselves in the middle of that with their ARP poisoning attack. And you can see here that these are the devices involved. So we've got 1.90 and 1.43 are the two devices that it's sniffing, and 1.11 is the attacker device. So what we want to do, we want to put another filter in here now that will say IP address is 102.168.1.11. So everything from that, and either 102.168.1.43 or IP.addr 102.168.1.90. So that is everything from the attacker and either its victims. If we see that, that is, I'll scroll back up to the top. Looking at this, this is mostly port 80 traffic, TCP port 80. So then we can see HTTP happening here. Doesn't seem to be much else going on. It looks like it's just HTTP traffic, and actually looks to be just between .11 and .43, which again kind of just points us towards 1.90 being the gateway here. All that is doing is routing traffic. 143 looks to be the target, and 111 is the attacker. This is HTTP, so we can also limit this down so we can see a little bit more what's going on. We don't necessarily need to see the handshakes. If we expand down here in the HTTP protocol section, we start to see some information around the hosts and that are being requested. Sorry, that's the response. So we can see the host there is devxcorp.net. devxcorp.net. Again, we can see all of that. So one other way we can do this a little bit clearer, highlighting this host field here, we can right click and say apply as column, and then we can actually see those results in the packet summary itself. So we can see that it is, for some reason, the victim is sending HTTP requests to devxcorp.net and the attacker is responding. We can see it, and then it's index.html, and then there's this getUpdate.exe. Now, okay, that kind of tells me that that's what's going on there. It doesn't really explain to me why that has happened. Why is this 143 suddenly talking to that on HTTP? There's nothing really in there, so I'd like to know a little bit more detail about that. So if I just edit this filter slightly, and I want to see everything from 1.43, and I want to see the DNS traffic. What is happening with that DNS traffic? So we can see 1.43 is generally talking to the DNS server 8.8.8.8, so that's Google's DNS. Nothing particularly wrong looking there. However, let's look a little bit more closely at what is actually happening here. If we look at the MAC address, why is that expanded there? Look at the MAC address of 8.8.8.8 there, and it is, sorry, I'm not sure if I'm looking at the right thing, 8.8.8. The device that's responding is actually the MAC address of the attacker. So you can see it coming out to there, so that it's being sent from the victim to the attacker, and the attacker is responding as if it is the DNS server, as if it is Google. So you wouldn't normally see that happening there. You might see the gateway there, but that is the attacker IP address. So the attacker is responding with the DNS. So there's some DNS spoofing going on there. We can have a look at some of the replies that are going on to find out what is the answers being given to these DNS queries. Because if the attackers are in the middle of this, is a DNS spoofing attack going on, the attacker is in control of what those replies actually look like. It could give the legitimate answer, or it could give an answer under its own control, so it can redirect users wherever it wants to be. In this particular case, it looks like the victim is looking up some Windows Update domains, and it looks like it's being given they look fairly legitimate here. If we do something we did earlier on, actually, just take it back up here a second. I'll open up the query here, and I will add this as a column. So this is the DNS query apply that as a column, we start to see actually what has been queried here. So we know that the Windows Update seems to be giving legitimate answers. If we have a look at DNS Google, the answers being given there, they look okay as well. Yeah, they're Google's DNS service. Similar here. So the attacker is sort of sitting in the middle of these conversations in control. Again, looks okay. So we can keep scrolling through, and then we get to this DevX Corp. That's the one we saw the victim going to, and it was the actual attacker's web server that responded. So this is probably where we're going to see the actual DNS spoofing attack really kick in. So the response to that, so this is outbound, this is the response, and the answer here, you can see that the address is actually 192.168.1.11. So that's why we saw that HTTP traffic going from the victim to the attacker, is because the attacker got in the way of their DNS queries and decided to respond with their own address as for this particular DNS request. We can, to go back to this, which spoof domain was accessed by the compromised user. So this is the spoof domain here. And we saw it being accessed when we looked at the HTTP traffic. So again, I'm going to copy the value of that, enter it in here, and we are good. Before the attack, the victim accessed this domain's legitimate web server. What is its IP address? And we don't have that information in the packet capture. The packet capture is just the information that happened during the attack, nothing that happened before it. So we need to find this in another way. We've got the disk triage artifacts from the victim, and inside that there will be some cached Chrome data. So inside our C users, user is the victim here. We can find our Chrome cache, not inside here, inside local, Google, Chrome, user data, defaults, cache data. So this is all of that's the Google Chrome cache. We need to be able to read that to find out what websites were visited by that browser leading up to the attack. There is a tool that can help us with this. It's by Nersoft. It's called Chrome Cache Viewer Tool. I'm just going to grab my link to this here now and download that. Nersoft.com utils Chrome Cache View.zip, and that's just going to come straight down here. Let's extract that to the same folder we're in. And we can open that up. So we want to actually open what we found earlier on, not this device's cache, but the artifact. So download, cafe poisoning, artifacts, desktop, C, users, user, app data, roaming. No, did the same mistake again. Local, Google, and we just go endlessly through these folders. Chrome, user data, default, cache data. And we can open that, and this is the cache of the Chrome browser from the victim. So we can see all the typical things you would expect to see with web traffic going on here. We want to look for something quite specific. There's a lot of entries here, so we want to look for the URL that was visited was devx-corp.net. So I'm going to just do a Control F and just search for the string devx. And we can start to see some things happening here. So this is a Google search where the victim has started to browse, or search, sorry, for devxcorp.net. So it's still on Google at the moment there. And here we actually see them go to devxcorp.net. So that's they follow that Google link and they've gone to the site. So if we follow this over, we can see it's an Apache server, 200 response, and there is the IP address. So that is the IP address of the actual server, not the attacker, which has intercepted it. So I can right click that, copy the clicked cell, and then we have got that. Great. Identify the Wi-Fi network name, or SSID, and the authentication algorithm used by the compromised user's connection. So there's a couple of things that we could do here. We could use RegRipper. That's one way to quickly extract information out of a registry against various plugins. It usually looks for quite specific things, but there's endless things that RegRipper can be used for. In this case, though, I'm just going to use the Windows Event Viewer. There is a Windows Event Log. Let me just find where it might be in our artifacts. The Windows Event Logs will be in our disk triage. So see Windows System32 Win Event Logs. And there's a whole bunch of things here, of course. But there is a Windows Event Log related to Wi-Fi connections. And it's this one here, WLAN autoconfig operational. So we can just open that straight up in Event Viewer. And there's a bunch of tools that will help us analyze Event Viewer a lot more simply, I suppose, than the GUI. It can be a little bit clunky. We'll come on to some of those a little bit later. But in this particular example, there aren't many events in here, so this works just fine for us. Now, the event ID for a Wi-Fi connection is 8001, and a disconnection is 8003. But we want to know when they're connected. So let's look for 8001. And there's only 2 entries, which makes it nice and simple. Only one of those is on the date that we're interested in. So we can bring this up a little bit. Open up the details so we can see the SSID is this Kappa C. And the authentication algorithm is WPA2 personal. So let's copy that. And the format of this is SSID : and then the authentication algorithm. Great. Identify the download link used to fetch the malicious executable. Now, if we recall, in our Wireshark traffic, we saw, go back to the HTTP, we saw this getUpdate.exe. Within the packet details here, we can see that was the URI request in it, HTTP 192.168.1.11, which we know is our attacker, update.exe. So we can copy value and we've got our answer there. So the story so far, we can tell from what we've seen here, is that the attacker has basically set up a rogue access point in some sort of internet cafe or just generally coffee shop. Once on that network, they perform some discovery scans and an ARP poisoning attack. With it, using that ARP poisoning, then they then spoofed DNS traffic and posed as a website that victim was going to anyway, put their own address in there instead, and convinced them to download this update.exe. We can actually also, now I think about it, we can see this index.html as well. So that could be so interesting going on in here. So we could start to have a look at what these files are, what convinced the person to browse to them, this and download the exe in the first place. So I went a bit quick there, but we can download files out of packet captures. So file, export objects, HTTP, because this is coming from the HTTP traffic, and index.html. Save that in our artifacts folder. Close that. Let's have a look at what actually convinced the user to go here. So that is what the unfortunate victim saw when they went to a website that they thought they already knew, devxweb.net or whatever it was. And they then clicked on this download update link, which took them to download the update.exe. Not there. Yeah. So that's the story so far. Identify the IP address and port number of the command and control C2 server. So we need to start thinking about inspecting this file to get here. So while we've got this window open, why don't we save this too? And let's start trying to figure out what this file is actually doing. One of the first things I like to do with a piece of malware like this is run strings on it. I am on a Windows machine, so I am going to use, I've got the sysinternal's strings tool installed. So I'm going to use that, sysinternal's strings, no, not streams, strings, except EULA, because that tells it to not do the pop-up. No banner. Look at update.exe, and I'm going to pipe that into more so it allows me to page through the output. Okay, so nothing hugely interesting there so far. Let's keep on going a little bit. Okay, so we've got some stuff happening here. So we've got a PowerShell command, PowerShell execute policy bypass, and then commands us running something after that. We've also got this string here, which looks just like a base64 encoded string. So we'll unpick that in a minute, but in the meantime, let's carry on going. Oh, we just missed it. There's a PDB file that's being mentioned. So it's the project for the binary. These look like Windows API functions and DLLs. There's not really a huge amount here that looks to be telling me about any kind of hard-coded IP addresses or anything like that. So the thing most of interest there was that base64 address. So let's have a look at that, see what that is telling me. Okay. Okay, so there are lots of ways of decoding base64. We could do it in PowerShell. It's a little bit clunky in PowerShell. I like to just something like this, base64 decode. We could use CyberChef. We could use all sorts, but yes, I agree to everything you want me to do. Okay, and that is telling us to, it's interestingly enough, add MP preference excluding pass C. So that's a Windows Defender basically bypass, exclude everything on C. Okay, so that's what's going on there. So that's quite interesting. But it's not giving me an IP address and port number. That's not what we're after at the moment. The other thing we can do is let's get the file hash of update.exe and let's see if anyone has already done any dynamic analysis on this using any.run. So you can go to the reports anytime you upload anything to any.run. If you've got a public account, it becomes public. That's always worth knowing. Don't ever upload anything that you is confidential in any way. And there are private accounts for that kind of thing. So we can put the hash into here. and do a search, see what's gone on. There's quite a number of them, all look to have the same file name, so people have probably uploaded this as part of this challenge. And so this is quite recent, so I'm going to pick this one. So if you're not familiar with any.run, it's an online sandbox utility. It allows you to upload binaries, give it some configuration details. You get slightly more with a paid account, but this is a free account that you're looking at here. And it'll give you information about network requests that were made, HTTP requests, DNS requests, process information. It'll tell you if Yara rules were triggered as part of it. You can see screenshots of what was happening. So you can see here that this particular piece of malware loads up with prepares updates, do not turn off your computer, and that continues. And if you remember, that's exactly what happened in the scenario. They loaded some updates and it carried on sitting there. So this looks to be the same binary as doing this PowerShell execution policy bypass command, and then is what are like Chinese characters, but I'm going to assume that that is the same exclusion that we saw base64 decode. In the HTTP requests and connections, there's a lot going on in here, but there's this little box that says hide whitelisted. We tick that, we can simply see update.exe making call out to 3.135.79.72 on port 5078. That looks pretty indicative to me. That's something that's interesting enough to make me think this is towards the answer. From a DNS request point of view, there's also Surex update.xyz. Again, that looks potentially like a call to the challenge author who's got a similar handle to that. So I think we're onto something here. We need to find the C2 address and port number. Now, when first doing this challenge, this was my instinct that this is the IP address and that is the port number. However, you can see here, if I input this, and the port was 50, it is not accepted. Now, I don't really know why. I mean, it's clearly calling out to that. It's not calling out to anything else. Now, I was putting myself in the shoes of this being a kind of situated challenge, and we know in this case that the attacker's IP address is 192.168.1.11 because we saw that doing the ARP scan, the ARP poisoning. We saw the malicious web server hosting the update there. So why wouldn't that also be the C2 server? Was my way of thinking, and on that same port, and then that is the answer. Now, I highly suspect that is not the intended route to the answer here. If you found a different way to do this, and that is much more likely to be what the author intended, even if you are the author, please do leave a comment or reach out to me, DM me on Discord, and we'll figure this out. That does seem to be the answer, but it's not what I could find. But nevertheless, we can move on from there. But please do let me know if you have another way. The malicious executable is designed to check the C2 server before connecting. Provide the domain name of the C2 server. Now, we did see that DNS request out to this domain from the binary. So we can copy that. And there we go. So that is much more accurate. The malicious executable verifies privileges before execution to ensure it runs as administrator. Which Win32 API function is used for this check? Now, this is where I decided I wanted to use Claude for this. So not necessarily to find the answer. The goal for me with using AI and CTF challenges is to use it almost like it is a much more focused search engine, if you like, or help me find the answer myself. So I don't want it to tell me the answer here, but I want it to tell me, what should I be looking for within that binary. So what I can say is which Win32, let's do it. So I've got Claude open here. Which Win32 API functions can, what's the way it's phrased? check if the binary has been run, oh my god, as administrator. Okay, so we can see here, then we've got two to think about. Is user admin? Check token membership. They are the functions. Does this tell me where they come from? No. Which DLLs, or which libraries are these two functions in? So I want it to tell me which DLL should I look to be imported to find out if they are in there. So get token information is in ADV API 32.dll. Is user an admin is in shell 32.dll. So what I can do here is have a look at my binary, see which functions, see which DLLs it's importing, and then which functions from those DLLs it is using. So to do that, but by doing that, we can confirm which of those two are the actual answer that we're looking for here. So to do this, I will close some of these because it is distracting me. I'm very sorry. I'm going to use Ghidra. And let's run that as an admin, which of course means in the background it's going to be checking one of these APIs. And we can agree to that. As much as I need help with Ghidra, I don't want that right there, right now. Okay, so we can create a new project. And we'll call it Cafe Poisoning. We can import our file to it. So where are we? We're in downloads, Cafe Poisoning, artifacts, update.exe. Portable executable looks good. Okay. Okay, so that's now finished. We can click OK to that. And now we drag our file over to the code browser icon and let that come in. Yes, we want to analyze, and then move that over here. I'm just going to pause the video while this does its analysis. Okay, so that has now done all its analysis, and we want to be focusing in this section over here. So I'm just going to close some of these, and in the symbol tree, in the imports, that's where you can see what libraries are being imported into the binary, and then what functions inside those libraries are actually being imported. So there were two we were interested in. It was shell32.dll, and we were looking in here, we were looking for is user an admin. And that is not being imported. So that's not what we're looking for here. So it pretty much leaves us with the other one, which is this ADV API.32.dll. We expand that and we can see this check token membership. Now that is the other API that Claude told us could work. So that's the Windows Win32 API function that will do this. So let's grab that name and enter that in here. It needs the brackets for a function, and we've got that answer also. Which command was executed by the attacker to disable Windows Defender? Now, okay, I'm going to close out of this a second. For this, we want to look at our more Windows event logs, our PowerShell logs. We want to know Windows Defender being disabled is likely to be a PowerShell command. There's an entire sort of set of commandlets that will control Windows Defender. So what we need to do here is load in our Windows event logs into a tool called, it's one of the easy tools, Eric Zimmerman tools. We'll be touching on these a lot in the next few questions. But this evtx xe command that can convert Windows event logs into CSV files or JSON and do all sorts of things with them. And so that's what we're going to do here. So I'm going to open a PowerShell command here. And call the easy tools net9 evtx ecmd evt. Right, okay, so that is the path finally we got there. So we have a look at that. We've got some the menu here. What we're going to be doing is taking the Windows PowerShell event log, converting it into CSV, and then loading that into Timeline Viewer for much more easy parsing. So we start that with -f. Now you can point this in an entire directory of event logs if you wanted to do it all at once. We could do that. We won't in this case. But we certainly could. I think it'll just add too much noise in this at this point. So we're in F, we're in artifacts, so we want to browse to our C, Windows, System32, Win Event, Logs, not application. Let's go. I think PowerShell starts with Windows, not Microsoft. Yeah, Windows PowerShell. Great. So we found that. We want to say, do it in CSV format and drop the file in this folder. And we also want to do CSVF and give it the file name. So we want to call this PowerShell.csv. Okay, so we just run that and let that go. And that is done already. So now we can open Timeline Explorer, which is another Eric Zimmerman tool. And we'll run that as admin and load in that CSV that we have just created. So in our artifacts, we've got PowerShell. And in our payload data 1, we've basically got the commands being run in PowerShell here. So we can start scrolling through, looking at various things that are happening. This is where we saw that execution policy bypass command earlier on, we saw in strings. But then we've got this update PS1. Now we don't know where that is, but that sounds reasonably suspicious. It looks to be the same time as our events earlier on. If we look over here, Same sort of time as we saw everything happening earlier. So this is interesting. So I would like to have a look inside that file. I need to know where it is, because this doesn't really tell me where it is. Just tell me where it tells me it's run from the local directory, but I don't know what that local directory is. So we can find out where it is on the drive by using another of the Eric Zimmerman tool suite, MFT CMD, I think it's called. So the MFT is the master file table. It is basically a big database that contains all of the information about files and folders on the device, on the operating system. It's a huge forensic treasure trove, and that's what we're going to be looking at here. So this particular command does a very similar thing to the one we saw just now. So it'll convert the MFT. Well, it can do lots of things. We are going to use it to convert the MFT into CSV, so we can again load it in and find out a little bit more about that update.ps1 that we just saw. So .f point it to the MFT file. So that is in C, and MFT is in the root of C, so we can scroll through that, and there's our MFT. Once again, we want that CSV, and in our local drive, at CSVF, the file name we want to call it is mft.csv. And that shouldn't take very long, and it did not take very long. So let's go to Timeline Explorer, MFT, great. So here you can see this is a whole load of information about the files and folders. There's parent path, the file name, the extension, the size, the date they were created, last time modified, last time changed, last access, all sorts of information about every file that is on that system. We want to know specifically about update, a file called update and the extension ps1. And here is that file. So it's in C users user downloads. Now, an interesting thing here is that, well, we can see it's created at the same sort of time within our time frame as well. So that also makes it very interesting. But the file size is actually only 61 bytes. Now, for the MFT, if a file is under 1024 bytes, the actual file contents will be stored in the MFT as well, which means that we can inspect the file, the actual contents of that file. I want to know what's in update.ps1, and we don't have it in our triage artifacts, but this is a way we can get hold of that just down to it being so small. There's a few ways we can do that, but you'll never believe me when I say it. There is a Eric Zimmerman tool to help us with this. So we will use MFT Explorer to open up the same MFT in a GUI, and we can start browsing through through that. We can load MFT. We find the same thing we did before. It's in the root of C drive, MFT, and we click go. Now, when you're doing this on a production system, this will take a very long time. Even in a small scenario-based challenge like this, MFT Explorer still can take a very long time. So I'm going to pause the video and I'll come back to you when it is completed. Okay, so that has now loaded, and we can see, you can see here, this is a little bit like Windows Explorer, like the name would suggest. But we've got a lot more detail around all of these various entries in the MFT. The file we're interested in is in C users user downloads, and then we've got our update.exe as well as update.ps1. That is the one we're interested in. And looking in the overview here, this is the text inside of that file. Set MP preference, disable real-time monitoring, true, verbose. that is the PowerShell command to disable Windows Defender. Set MP preferences, how you turn on and off various features within Windows Defender. So that's what that is doing here, disabling the real-time monitoring. So that is our answer for this. A persistence mechanism was created by the attacker. Provide the registry key used for persistence. If we go back to our MFT, we know that this update file was created around about this time. So a thing we can do, or we should do rather, is have a look what else happened around this time. What other files were created around this same sort of time? So I've just removed the filter and I kept that line set so we can see where we are, and I want to set this in created order. So that is now in ascending order. That's what we want. So let's go back to these file names and let's have a look what's going on. So shortly after update.ps1 was run, we can see a couple of things here. So if we look at if I just expand the parent directory, this cryptnet URL cache, that usually indicates things coming down for using certutil. Certutil being basically a living off the land binary. Is a binary built into Windows that attackers can use to bypass certain security measures and download things from the internet. Cryptnet URL cache is often seen when that is run. There is this file screensaver.scr created in C Windows System 32 shortly after, and then we've got these prefetch files for certutil. So a prefetch file is created every time an application is run. It's a Windows functionality to allow applications to start up more quickly, but it's also a good forensic artifact because it will also tell you when an application ran. So we can see that certutil was run around this same time. More screensaver entries, and then reg.exe also has a prefetch file run around the same time. So that's sort of indicating a little bit there that certutil was used to download screensaver.scr, and then the reg.exe command was run to do something with that. Screensaver is stored in the registry, and we can have a look at our registry to find out whether this screensaver.scr is actually set in there, because that can be a persistence mechanism. So if we just Google for screensaver persistence, so you can see here the MITRE entry, event-triggered execution screensaver. So it can be a privilege escalation or a persistence. And that is set in HKeyCU or HKey current user, control panel, desktop. And you can imagine that being a persistence mechanism. Every time the machine goes idle, if there's a malicious screensaver set or a malicious file acting as a screensaver, the computer goes idle, Windows initiates the screensaver, and then the attacker gets this callback to the C2 or anything that malicious script is doing instead of being a screensaver. So we should check this location and see whether we can see indication of this file being there. And you aren't going to believe me when I say it, but there is a Eric Zimmerman tool for this, Registry Explorer. And I've just opened it, and I should have opened it as admin, so you'll have to excuse me while that opens and I close it again. The HKey current user is the local user profile. So that is stored in the ntuser.dat of the user that you're investigating. So the enter-user.dat is inside the user's directory, inside user, and we select enter-user.dat. Load that in here. This is asking me, it's saying there's some uncommitted changes in this, and there's some transaction logs. Do you want to load those as well? Yes, we do, because then we get the most up-to-date version of that registry hive. These two log files here are what we're interested in. They're the transaction logs. Yes, we want to save the clean version, so that's the updated version of this. It doesn't matter where we save it. I'll just save it alongside the rest of the challenge artifacts, but that really doesn't matter. Yes, we want to load the updated version of what we've just done, and we don't want to update the original version I selected because that's the dirty version, as it calls it. Right, so we've got that open now. So if we remember where this was set, HKey current user, control panel, desktop. So let's have a look at that. We're in HKey current user, control panel, desktop. And these are all the various things that happen within control panel here. And we can keep scrolling. And right at the end, we can see screensave.exe and C Windows System32 screensaver.scr. That is the file we saw being created very shortly, or less than 1 minute after update.ps1. It's in the same part of things that the compromised user was operating, and that indicates that this was set as the persistence mechanism. So if we look at the format that we actually want to give this answer, because registry keys can be a bit funny. Sometimes they can be referred to as HKey current user, control panel, desktop, or HKCU. So looking at this, that looks to be formed in the same way as the way Miter's described it here. So I can copy that. And that is cafe poisoning done. That wraps up cafe poisoning. Thank you for watching. If you like, please do like and subscribe and all that usual good stuff. If you managed to solve any part of that Sherlock in a different or better way, please leave a comment, especially that question in this that was a little tricky, and I really do think I came to that in an unintended way. I'd love to hear more about that. Please do check out Sherlock's on HackTheBox. There are over 100 available to play. Many of them are free. We release a new one every Thursday. For now, diolch yn fawr.